Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. Okay, so previously we have learned the theory on the compression members or column. So in this video we're going to learn how can we design concentrically loaded columns. But bear in your mind that a concentrically loaded column is rarely exists in the real situations, and this is because the end restraints for most of every columns are rarely perfectly pinned or perfectly fixed, and the load is not perfectly concentric. This is a very basic column design example, and actually you have done this before when you registered for basic steel and timber design. Okay, let's now start with this first example. Okay, so now let's look at the questions. So basically this example is taken from the steel work examples from the SCI United Kingdoms. So if you look at these examples, it is pin column using a class 3 sections. So here if you look, the column shown in figure 9.1 is pin ended about both axes and has no intermediate restraint. Design the column in S355. So when it says S355, it means that your grade of steel is S355, and this is the parameter of the columns. As you can see, here is the NED concentrically loaded. Okay, and the length is 6,000 millimeter, and this is the plan view where this is ZZ and this is YY, minor axis and major axis. And you need to have the references for BSEN 1993 Part 11 2005, and according to the national annex unless otherwise stated. Alright, so what does it mean by these columns? If you look for these columns, okay, the idea of this column is this, whereby you have single columns, okay, which is this is the ZZ axis and this is the YY axis, and you have the load acting concentrically loaded, meaning that it is acting directly on top of the centroid of the columns. That's what it means by concentrically loaded columns. So what happened if you have another if your loading is not loaded directly on the centroid of the cross-sectional area of the columns? Then you might have the eccentricity. For instance, if you look this column. Okay, so if you look at these columns, okay, this one, what is the difference is that if you look at these columns, okay, this is the axis. Alright, you can see this is the Y and Y axis, and this is the Z and Z axis. So if you look at these columns, okay, the load, this is the load, NED. Okay, so the load is acting at a certain distance from the centroid. So this is the centroid of the cross section of the columns, and the load is acting at a little bit about certain meters downward from the y-axis, okay, from the neutral axis. So that is what we call as the eccentricity. So when the load is acting at certain eccentricity distance, okay, to the centroid, therefore the load is not concentrically loaded, hence these types of load will cause a moment to the y-axis. Okay, so let's now look at this question. So I have shown you the idea on the three-dimensional view of this particular questions. So now let's look at the solutions. Okay, what we will do in these examples, okay, so in this example, the design aspect covered in these examples are, first, how you determine the cross-section classifications, and I am very sure all students able to do this because we have many times do the cross-section classifications. It is similar like what you have been applying for topic beams, and composite, and so on. So the cross-sectional resistance, meaning that you need to check whether the beam, okay, whether the columns, okay, these columns, okay, whether these columns, it is whether the cross-sectional section that proposed for this column, okay, able to resist the compressions, okay, and then you need to check the buckling resistance of these columns as well. You need to check whether it can resist flexural, torsional, and torsional flexurals. So if you need to know, if you want to know what is means by flexural, torsional, and torsional flexural resistance, you can refer to the previous lecture, which explained about the buckling resistance or buckling types of failure for a compression member. Okay, next let's look at the design value for ultimate limit state. So the design compression NED is given 3500 kilonewton, okay, and the section choose for this particular columns, okay, the section choose for this particular columns is 368 times 129 UKC in S355 steel grade. Okay, so for these columns, okay, you can get all these sectional properties referring to your UB, UC sectional dimensional properties books. So you can have this, okay, and you can get the E and G value, and this one you can have from the Eurocode itself. Okay, alright, so basically this is all about the properties of the column. Alright, so once you have done the properties of the columns, okay, we now know that the properties of the columns can be found in the dimensional properties table. So now we can start off with the cross-section classifications. Okay, this is our first task, which is cross-section classifications. So as I said earlier, the cross-section classifications, you are familiar with it already. You can refer to table 5.2 BSEN 1993 part 1.5. Okay, and here you can see what is your FY, which is 345. Okay, and then you can refer to the outstand of compression flange. Okay, the outstand of the compression flange, you have C and B minus TW minus 2R over 2, and then you finally get 163.9. So that you can you need to check for C over TF. Okay, so it goes to the table 5.2. okay, you go to the table 5.2. okay, you need to go to table 5.2, where this is table 5.2 in the Eurocode. So maximum width to thickness ratio, compression parts. So the compression parts, here is the C value, okay, and this is the outstand of the web, internal compression parts. So here how you calculate C is equivalent to B minus TW over 2R, which is, if you can see here, this is C, whereby, sorry, this is this one, C. Okay, you can calculate for compression part, and then for the outstand flange here, whereby your C is equivalent to B, okay, minus TW, alright, and minus 2 root radius, so you can get this C value. Okay, however, if you're not analyzing this by using the equations, you can still find the C over TF and C over TW values by straightly look at your section dimensional properties. So then you can check whether your C over TF is less than or not. So in this particular case, for the outstand flange, okay, so once you calculate, you get C over TF is equivalent to 9.37. okay, whereby you need to check whether, okay, the C over TF, okay, is less than 9 strained or less than 10, okay, or it is in between this 14 string. So once you check this, okay, you check C over TF less than 10 string, which is your string is 0.83, taking from here, then you get 8.3. So it means that your C over TF 9.37, it is not less than 10 strings, okay, because your 10 string is only 8.3. So then it means that it's not fall under class 2, okay. So then you have to check, you need to lower down your class, okay, class to class 3. So then you check here your C over TF, which is 9.37, okay, is less than 14 string, which is 14 string is 11.62. So then 9.37, okay, which is this, is less than 11.62. Therefore your conditions, okay, the flange in compression is class 3. Okay, that is how you get the class 3 for your flange. Okay, students, similarly for web subject to compression, again you need to refer to table 5.2. okay, so this one, this table. So web subject to the compression members, okay, compression parts, where this is your C, okay, where you can calculate your C by having that C over TW, or you can take your C is equals to D, okay. You can, some engineers, they just take C equals to D, okay, or you can, to be accurately, you can minus the root radius as well, but both we can accept. And also you can get another things from the section dimensional properties, where the ratio of C over TW. So in this case, your D is 292.0 divided by your thickness of web is 10.4, so that's why you get the ratio 27.9. So 27.9, okay, 27.9. So you need to check here. The main difference in the compression member is that you need to make sure the cross-section classifications is part subject to compressions. Okay, for column, the compression part, which is the web, okay, the web is subject to compressions, so you need to go through this column, okay, instead of this. This is for beam, because for beam your web is subject to bending, okay, but for column your web is subject to compressions, okay. Alright, so here you need to check your C over TW, whereby your C over TW is 27.9, okay. So the 33 strain is 27.39, which means your 27.9 is not less, okay, it's not less than 33 strain, which is 27.39. So therefore it's not fall under class 1, okay. C over TW 33 strain, so it exceeds the 33 strain value, so you need to lower down your class, okay, by checking with 38 strain. So when you check for 38 strain, you can see that it is 31.54. so C over TW, okay, which is less than 38 strain, okay, so therefore you get 31.54. So since your C over TW, this is C over TW, is larger than 33 strain but lesser than 38 strain, okay, 33 strain and 38 strain epsilons, so therefore the web is class 2 under compressions. Alright, so as I explained to you earlier in previous chapter, okay, since in this case your flange, okay, your flange is classified as class, your flange is classified as class 3 and your web is classified as class 2. So in this case you need to choose the lower classes, okay, which is the section is class 3 under compression, so you need to choose this. Okay students, so now let's check the second verification that we need to conduct, which is cross-sectional resistance of the compression members. Alright, so according to BSEN 1993 Part 2005, it says that the compression resistance you need to refer to clause 6.2.41. Okay, where if you can see, this is the clause for the compression member resistance. Okay, the design value of compression force NED at each cross section shall satisfy NED over NCRD less than 1, which is given in equation 6.9. So here you need to verify that the cross-sectional resistance of your column that you propose must fulfill these conditions. Okay, your NED over NCRD must be lesser than 1. So there is no issue to find NED, because you already know that your NED is equivalent to hold on, let me check what is your NED value is. Okay, so your NED value is given as 3,500 kilonewton. Okay, in the questions, it's already given in the questions, which is 3,500 kilonewton. So here, when you look here, the design resistance of the cross sections for uniform compression is NCRD is given. So NCRD is given as AFY over gamma M dot for class 1, 2 and 3 cross sections. So in our case is class 3 cross sections. Okay, so you can refer to equation 6.2 here in BSEN 1993 part 15. Alright, so in these equations, so you can have NCRD is given as this. Alright, so substitute the value where you have the value from the cross-sectional properties in the earlier message, where let me check here. Okay, 164 cm. Okay, so you get 164 times 345, which is your cross-sectional your Fy value over 1. Okay, gamma M naught, which is times with negative to the power of 3, you get 5658 kilonewton. So therefore you substitute this value into the equations. Okay, and then you will get NED over NCRD equals to 0.62, which is less than 1. Then you can conclude that the compression resistance of the cross section is adequate. So in your notes you can refer all these clauses, okay, which given the detailed explanations on this parameter, whereby you can look at this. Okay, NCRD, what is NCRD? So it's given for class 2, class 3 and so on. Okay, so please refer to your note as well. Alright, so in our list of verification check, we can now say that the cross-sectional resistance due to compression, okay, which is this, the cross-sectional resistance due to compression, NED over NCRD less than 1. So we can highlight it here, whereby NED over NCRD equals to 0.62, which is less than 1. So then it satisfies the cross-sectional resistance. Therefore we have done this, we have then done that. So the next check that we need to carry out is what we call as a buckling resistance checks. So let's do this. Alright student, so the next check is our buckling resistance of the compression member. So for buckling resistance of compression member, you need to refer to clause 6.3, which is this clause 6.3 in Eurocode. So for clause 6.3, so uniform members in compressions, so you need to check member buckling resistance NED over NBRD. which means NBRD is the design buckling resistance of the compression members. So, design buckling resistance of the compression members is given in equations here. The design buckling resistance, okay, of compression member should be taken as either equations 6.47 or 6.48. So again, if you are dealing with class 1, 2 and 3, so your NBRD is equivalent to these equations. But if your cross section is class 4, then your NBRD must to take into account the effective area of the cross sections. So in this case, okay, if you look at your examples, so you need to verify NED over NBRD as mentioned in the Eurocode. NED over NBRD. So NED over NBRD, okay, in your case your class is class 1, so your NBRD is equivalent to these equations. So for these equations, you need to find what is your reduction factor. This is what we call as the reduction factor. So basically you need to find what is your reduction factors, okay, and the way how to get the reduction factor is quite long and extensive. So if you like, let me derive it for you, okay. So basically your NBRD is equivalent to reduction factor times with the area times with the Fy over gamma M1. Okay, so then you need to find what is your reduction factor, because here you can get from the section properties. Here you can get from section properties, and you already know what is your Fy value and what is your gamma 1. Okay, so this is 1.0, and here you can get 3, 4, 5. Okay, so here reduction factor. So reduction factor is given in this clause. Okay, if you look here, buckling curve. Okay, the reduction factor is given as these equations. All right, so reduction factor. And to get this reduction factor, you need to find another parameter, what we call as the phi, by having these equations. And to get phi, you need to get the lambda. Lambda is given for these equations. So it's quite a long procedure, okay, for you to get the reduction factor itself. Alright, so it means that I will write here your reduction factor is given as 1 over phi plus phi squared minus lambda squared, lambda bar squared, okay, and must be less than 1. So for you to get this, okay, you need to find what is your lambda, sorry, what is your phi, and phi is equivalent to 0.51 plus alpha lambda bar minus 0.2 plus lambda bar squared. And then you need to know what is your lambda, which your lambda is equivalent to, in our case, is our class 1 to 3. So lambda is equivalent to A Fy over NCR square root, which is lambda bar is equivalent to that. Okay, so this is how you wanted to get what is your NBRD. Okay, so here, therefore, in this you need to find what your NBRD. So NBRD, first you need to find this, okay, this parameter, okay, where the reduction factor for the buckling curve n is determined from this, okay, and if you look at the next page, phi is equivalent to this parameter, as I explained earlier, and lambda is the slenderness for flexural buckling, where you can get it from equation 6.3.1, equation 6.5450, lambda, and then lambda is equivalent here, where you can get from here, and lambda 1 is 77.94. So slenderness for buckling about the minor axis. Alright, so in here you need to check for both axes, which is minor and major axis. Earlier, if you look at the so basically you need to check the buckling resistance of your structure in both ways, which is in ZZ axis and also in YY axis, which means you need to check whether there is a possibility for your column to buckle in these directions, or your column will buckle in these directions. Okay, so you need to check for this one. So in this case, you are checking for buckling about the minor axis ZZ, and you find what is your lambda Z. Lambda Z is equivalent to LCR over IZ times with 1 over lambda 1, whereby your LCR is depends on the boundary conditions of your column. To recall, if you refer to these notes, buckling length LCR, which in the previous videos, EC3 provide little information on how to determine LCR, difference, and restraint affect the buckling length of the columns. So the end restraint could be referred to table of buckling length extract from EC3 page 7, where it is depends on the end translational restraint or pin restraint, also called restraint positions, and these conditions whereby it is depends on the end rotational restraint. So what does it mean then? It means that in your case you have pin and ended, meaning that both are allowed to rotate. Both and allowed to rotate. So because both and allowed to rotate, therefore your effective length or critical buckling length is measured from the moment where the column is rotated, which means your LCR is equivalent to L. Just what we call it, restrain it laterally like this and allow for the rotations. And if I pull, if I pull here, so it will able to rotate from this distance to this distance. It able to rotate. But in this case, if you look at the second case, the second case means at the top allowed to rotate, but I fix at the end. At this point I fix it. So when I fix it, I fix it and I'm not allow any movement. So if there is a load pulling from here, so can you see that the angle of rotation start at the end of the member, but at this case the angle of rotations only start at certain distance. At certain distance. Alright, so in your case, because of both are pin, therefore L is equivalent to LCR. Since your L is equivalent to LCR, so LCR is taken as full length of your column, which is 6,000, and IZ is taken as 94.3, where you need to calculate your IZ, and then 1 over lambda 1, which is lambda 1 is 93.9 times the epsilon strained, where I give you 77.94. So in this case you get 0.82. Alright, so these equations you can get from equation 6.5. So this is equation 6.5. In your Eurocode, this is equation 6.5. If you can see, so you can see that lambda is equivalent to this. I is general here is not mentioning any Z or Y axis. It depends on your calculations. If you are checking on minor axis, IZ, so then you need to use IZ here. If you are checking for the major axis, which is Y, so I here must be IY. And from there you can get what is your lambda value. Okay, so once you get your lambda Z value, you are required to check according to 6.3.1.24, where in these equations, okay, alright, so 6.3.1.2 buckling curve, number 4, which is this, okay, number 4, for slenderness, which is in your case is lambda Z, if slenderness is lesser than 0.2, or for NED over NCR is lesser than 0.04, therefore the buckling effects may be ignored and only cross-sectional checks apply. So in this case, you check that your lambda Z is larger than 0.2 and your NED over NCRD is larger than 0.04. Therefore, you can conclude that the flexural buckling effects need to be considered. So meaning that you cannot ignore the flexural buckling effects. So what happens if it complies with these conditions? If your case comply with this condition, it means that you don't need to check for flexural buckling resistance. You just can do until compression resistance. That's what it means. Okay. Okay, students, so now you have determined the lambda value. So for you to get, now you have done this lambda value, so for you to get the phi value, you need to determine for another parameter, which is alpha, what we call as the imperfection factors. So for these imperfection factors, okay, for these imperfection factors, it is rely heavily on the section of your structures. So if you look here, this is the roll sections, and your structure is fall under these sections. They have another section as well, but all the other sections are not related at the moment for this particular example. So for this one, your roll section, you need to check your H over B limit. Okay, so H over B. So you can check H over B. If your H over B is less than 1.2, then you need to comply with these equations, and finally you will get what is your buckling curve. So now let's check what is your condition in these examples. So in this particular examples, okay, we check your H over B. For this particular example, we check for your H over B. So your H over B is 0.96, which is less than 1.2, and your thickness of flange is 17.5, which is less than 100. Okay, so refer back to this table 6.2. Okay, table 6.2, H over B, which is less than 1.2, and thickness of flange is less than 100. So you are now checking for buckling curve about Z axis, which is about minor axis. So therefore, your buckling curve for grade S355 is buckling curve C. So buckling curve C, you need to go to table 6.1, which is this table 6.1. Okay, imperfection factor, which is alpha value. Buckling curve C, imperfection factor alpha is equivalent to 0.49. So once you get your alpha is 0.49, so you can substitute all the equations. Lambda Z 0.82, alpha is 0.49, substitute in these equations, finally you get 0.99. And from there you can get what is your reduction factor. Okay, so if you recall this, you get your lambda already, your phi, which is your value, you already get it, and then substitute all this into these equations where you can get your reduction factors. From here you can get your buckling resistance. So here, if you look in these examples, your reduction factor after substituting all the necessary value, you get 0.65, and it is less than 1. So meaning that the design resistance for buckling, for flexural buckling, after substituting all the equations, you get 3, 6, 7, 8, which is less than 1. Therefore, the flexural buckling resistance of the section is adequate. So, in this examples, you then already satisfied the flexural resistance designs. So flexural resistance, we know that you need to verify NED over NBRD must be less than 1, which is adequate. So far we can confirm that your columns is comply the cross-section classifications, and it complies with the compression resistance designs, and in terms of the flexural buckling resistance, it's also comply. So there are another 2 more checks that need to be carried out, which is the torsional and torsional flexural resistance. So for this, you need to refer to clause 6.3, which is this. Okay, you need to refer to clause 6.3.14 for slenderness for torsional and torsional flexural buckling. Okay, so in this example, so meaning that you have to go through this in your Euro code and try to look at the clauses given to you. Okay, what is your lambda t and so on. Alright, so go back to your notes. So torsional and torsional flexural resistance, okay, is stated that for open sections, the possibility that the torsional or torsional flexural buckling resistance may be less than the flexural buckling resistance should be considered. Okay, so doubly symmetrical sections do not suffer from torsional flexural buckling. So in our case, we are doubly cross-sectional resistance. If you look here, okay, why we call it doubly symmetry? Because if you look at the y-axis, okay, this is your y-axis. Here and here, if they are mirrored, if we mirror them, they are the same length, sections, and so on. And if we mirror in terms of z-axis, here and here, they are also mirror, and they are symmetry. But what if we look in these examples? This is the C sections. If you mirror for y-axis, this and this, they are not symmetry. Sorry, they are symmetry. But if you mirror it in terms of the Z and Z-axis, they are not symmetry, because it's only in Z-axis. Here you have this, but here you don't have closed sections. So in this particular case, what I'm trying to say, for this particular example sections, okay, the cross section itself may be subjected to torsional and torsional flexural buckling. So meaning that the structure can twist, okay, and the whole lot also can able to buckle. Alright, so now let's look at our examples. So as I said earlier, you need to do the verifications for NED over NBTRD. So what is the NBTRD? So in this case, you need to verify NED over NBTRD. So basically, it is similar like what we have done before for the, if you still remember this, NBRD, which is the reduction factors times with area and so on. But instead of flexural buckling resistance, okay, you are now calculate for the buckling torsional resistance. Okay, so buckling torsional resistance, you have the same equations, but you need to find, instead of reduction factor alone, you need to find the torsional reduction factor. Here for NBRD, only reduction factor flexural, but for torsional, they have the torsional buckling reduction factor. So similarly here, you need to find this. For you to find this, you need to have this. For you to get to fulfill this, you need to find what is your slenderness torsional buckling, which is given by this. And for you to get this, you need to get all this. And for this, you need to find the imperfection factor. This is a similar way how you get for the flexural buckling, but this is for torsional resistance. Okay, so now if you look here, This is the equation that I explained to you. Okay, and here also the equation, the same equation I explained earlier. So now the most important part here, NCRT. What is the NCRT? NCRT, if you go for these equations, okay, in our Eurocode, okay, what we call as a non-dimensional slenderness for torsional. Okay, so you are referring to which cross sections are you considered now. In this case, you are in class 1, 2, 3. So this is NCR. So for torsional, what is the NCR value? You need to have this. NCR is equivalent to NCRTF, but NCR must less than NCRT. So what is NCRTF? NCRTF is the elastic torsional flexural buckling force. Okay, so how can you get the elastic torsional flexural buckling force? Okay, let's look at your notes. So here is the equations for you to get the torsional buckling force. So this is something interesting where you need to find, here is equivalent to these equations. I is the radius of gyration, but y exists, z exists, and y naught. Y naught is the distance from the shear center to the centroid of the cross sectional along the y-axis. So meaning that in this particular case, if you refer to the diagram here, okay, so your shear center for this column is coincident with the centroid of this cross sections. So in other way, it means that your y naught is equals to 0 because it is acting at the same point. However, if you are given a different sections, for instance this, you are given in the C sections, so your centroid, your shear center is here. Okay, and then you have the shear centers, and then you need to find where is the centroid. Okay, so here you need to get the shear center of your cross sectional area to the centroid. So then they have the difference y naught. Okay, all right, so in that particular case, okay, so for our case, your W symmetry section is 0. So I naught, then you substitute all the required equations. Finally you get 182.29. Substitute into the whole equations for NCRT. Finally you get this value. Okay, once you get that value, substitute it into the equations, then you get 0.72. Alright, so again, when you get this lambda t value, okay, just to recall, this is lambda t value. You already get your lambda t value, which is 0.72. okay, here is equals to 0.72. So then you can find this equation for you to get the torsional buckling resistance reduction factors. Substitute it into these equations, but unfortunately we're still not calculating for this. Therefore you need to find this. For this you need to find what is your alpha, which is the imperfection factor. So imperfection factor, again, it depends on the buckling curve and the cross-sectional resistance of your structure. So in this case, just check H over B 0.9, which is less than 1.2, TF 17.5, less than 100. So again, the same thing, less than 1.2, less than 100. For ZZ exists, your buckling curve is C. So when your buckling curve is C, you are now getting on the table 6.1. Sorry, for this one you need to refer to table 6.2. Okay, you need to refer to table 6.2. Oops, this is table 6.3. Okay, so here, oops, okay, so here you need to refer. So once you have referred to table 6.2, okay, so then go find the slenderness, the imperfection factors. So buckling curve C, you get 0.49. So therefore you get 0.49, which is this. Okay, 0.49. So once you get 0.49, again substitute all the equations into the required equations. Finally you get your 0.89. So here you get 0.89. Okay, you get 0.89. So 0.89 can be inserted into these equations. Finally you get what is your reduction factors. Your reduction factors, you substitute all the required parameter. Substitute all the required parameter into the equations, and you get 0.71, which is less than 1. And substitute everything into these equations, you get NBTRD. So your NBTRD is given as 4017, and it is less than 1. So the torsional buckling resistance is adequate. So this complete example 1. So to conclude, as for conclusions, we done for torsional, okay, torsional resistance, where your NED over N BTRD must be less than 1. So conclude for this example, meaning that in these examples, as a conclusions, the cross section is passed, the compression resistance is passed, and all the checking for buckling resistance is also verified, and they are all satisfied. Next video will be in examples 2.